evening, students, and welcome to today's session. So we will be continuing ahead with applications of first law of thermodynamics today. Last lecture we had seen polytropic processes in detail, and before that adiabatic process, isothermal process, etc. So we saw the general polytropic process as a family of curves on the PV space, and we derived a particular formula for that general polytropic process application of first law, including a formula for the molar specific heat capacity and also a formula for the work done and heat exchange during a polytropic process in terms of the particular equation of the polytropic process, or in terms of the relationship between pressure and volume. So let's take a recap of that concept, and from there we will continue ahead with cyclic processes and into heat engines today, cyclic process and heat engine type of processes, and with that we will wind up the applications of first law. So as I was saying, as one of the important applications of first law of thermodynamics, we have been looking at polytropic processes in the last lecture. So we saw the general equation of a polytropic process as a relationship between pressure and volume of the type PV to the power some real number being constant, where alpha can be any real number. And we saw for that we get the special formula that the molar specific heat capacity becomes CV plus R upon 1 minus alpha, or that is the same thing as F by 2R plus R upon 1 minus alpha. And heat supplied to the gas is obviously NC delta T, where the value of C is given by this particular formula now. Okay. And the work done by the gas also can then be defined in terms of this, like this particular equation. Okay. And further, we had seen that the standard 4 processes were special cases of polytropic process. Okay. So we saw that isothermal process is nothing but a special polytropic process for which alpha is equal to 1. So P into V is constant. So as we know, the molar specific heat capacity for isothermal process is undefined. And Q is therefore not given by this equation. Q is equal to W equal to nRT natural log of V final by V initial. Okay. Then we saw that isobaric process can be categorized as alpha equal to 0. So that means P is constant. So the molar specific heat capacity becomes CV plus R, which is nothing but Cp, which is nothing but F by 2 plus 1 into R. And the work done is nR delta T, which is the same thing as P delta V. So these two formulae are things that we are already familiar with for isobaric process. Okay. Similarly, we can see isoporic process can be thought of as a polytropic process where alpha is tending to infinity. So what happens is P into V to the power alpha is constant. Also implies that P to the power 1 by alpha into V is constant. So that means that in this, if we take alpha tending to infinity, it means that volume is constant. That's how it becomes an isoporic process. And for this, you can see C becomes Cv plus R upon infinity, basically minus infinity. So that becomes Cv or F by 2R, which we know is correct. Okay. And work done is nr delta T upon again infinity, which implies that work done tends to 0, which is also correct. So this, and then finally the adiabatic process is one where alpha is equal to gamma, or 1 plus 2 by F, or Cp by Cv, these relations. Okay. So anyway, so for this, what happens is that our molar specific heat capacity this actually becomes 0. Okay, because R upon 1 minus gamma. So this should be 1 minus gamma, because we substituted the value of alpha as gamma. So R upon 1 minus gamma is the same thing as minus F by 2R, because gamma is equal to 1 plus 2 by F. So from that you can see this. So molar specific heat capacity is 0, so Q is 0, and therefore work done is nr delta T upon 1 minus gamma, which is minus F by 2 nr delta T, or work done by the gas is negative of the change in internal energy. So again, these are facts that are known about adiabatic process. So we can even think of the 4 standard processes: isothermal, isobaric, isoporic, and adiabatic as special cases, or you can say as members of the general polytropic family of curves. Okay. But the whole point of adiabatic process, the whole point of polytropic process is it is not just giving us like a master formula for the 4 standard processes, but is giving us a master formula for any type of process where there is a relation between pressure and volume of the type PV to the power alpha is constant. So these 4 are only special cases of that, but there are infinite other possibilities for the value of alpha. So any process which can be described by a relation between pressure and volume of the type PV to the power alpha is constant becomes a general polytropic process, and we can therefore obviously use the formula directly for it. Okay. So we've seen some examples in the previous lecture also, but I will start with another example today, wherein the question is given to us in a slightly different way, and we have to understand how to interpret it. Okay, so this type of question becomes important, especially at the JEE Advanced level. So for example, in a given question, suppose what is shown to us is a relationship between temperature and volume instead of pressure and volume. Okay. So it's a process shown to us where temperature is varying with volume, and the gas is undergoing, let's say, an an expansion of this type, where temperature is proportional to 1 by square root of V. So start from the point A and going via this process where temperature is proportional to square root of volume, 1 upon square root of volume, it reaches the point B, where what is given to us is that temperature at A is equal to, say, 400 kelvins. Okay. Volume at A is equal to 1 liter, and pressure at A is equal to 1 atmosphere. Temperature at B is equal to 200 Kelvin, and AB is an expansion such that, already mentioned, temperature is proportional to 1 upon square root of V during the process. Okay. So if a sample of hydrogen gas is undergoing this process, okay, then calculate Q, delta U and W, okay, and plot the PV graph for this process. Okay. So the information given in the question is slightly indirect, and we will see how we can interpret this question in such a way that we can ultimately make use of the of the polytropic process definition. Okay. So just go through this question and try to figure it out how we can interpret this equation that temperature is proportional to 1 upon root V, or temperature is inversely proportional to square root of V. How shall we interpret this? Okay. Try to figure that out. Then we can understand all the other things.
Show me where we put a drip tray, a sluice, and an overflow reservoir. Hey, water is a ball. We're gonna have to ground the crap out of the thing.
Guys, it's hot in here. I think I'll just take off all my clothes.
Okay, so just as a hint, what I will give you here is that temperature is inversely proportional to square root of, or inversely proportional to square root of V. Now in this, temperature itself is proportional to PV, because PV is equal to nRT. Okay. So that means pressure into volume is inversely proportional to this. Okay. So in other words, PV to the power 3 by 2 is constant. So this is the interpretation. Okay. So we can see that therefore this is a general polytropic process with the polytropic coefficient alpha is equal to 3 by 2. So now we don't have to do any lengthy integration or derivational kind of solution of this. We can, once we have come to this equation that the relationship between pressure and volume is of this type, now we can quite easily directly apply the formula of polytropic process. And remember, it's given to us that it's hydrogen gas, so you can see it's a diatomic gas. Make use of that also. So try to work out this question now, including the last part, which is the pressure volume graph. We'll discuss this soon. So this is the level of application you have to anticipate for JEE Advanced level when it comes to polytropic processes. Okay, hope the question is clear. Yeah, Kunj, I'll verify your answers. They're correct. Okay. Anybody else who has got the answers? So see, we have to first of all understand that temperature is inversely proportional to square root of volume. That means that TA upon TB is square root of VB upon VA. Okay. And temperatures are given to us, right? Temperatures are 400 Kelvin and 200 Kelvin. Whereas the volume at A was given to us as 1 liter. So this tells us that the volume at B will become how much? Become 4 liters. Okay. Then we can use the fact that TA VA upon TA is equal to PB VB upon TB. So from this now we can understand that the pressure at the point B. Now the pressure at the point A was how much? The pressure at the point A was 1 atmosphere. Okay. So the volume is becoming 4 times, but the temperature is becoming double. So the pressure should become half. So the pressure at the point B should be PA by 2. So it should be 0.5 atmospheres. Okay. So now we know the state. We know that it's going from PA, which was 1 atmosphere, VA, which was 1 liter, and TA, which was 400 Kelvin, to final pressure of 0.5, final volume of 4 liters, and final temperature of 200 Kelvin. Okay, via this process where temperature is inversely proportional to square root of volume, or PV to the power 3 by 2 is constant. So this is the more important thing for us. So with this information now we can directly use the formula and calculate everything that is required. We can use these formulae that PV to the power alpha is constant, means Q is equal to NC delta T, where C is CV plus R upon 1 minus alpha. W is NR delta T upon 1 minus alpha. And obviously delta U is a universal formula. So delta U, it doesn't matter what the process is, it is always given by the formula NF by 2R delta T. Okay, so let's apply this now. So here we are talking about alpha being 3 by 2 and F being 5 because it is hydrogen gas. So it is diatomic in nature. So molar specific heat capacity will become 5 by 2R plus R upon 1 minus 3 by 2. So 5 by 2R plus R upon minus half. So 5 by 2 minus, so it is R by 2. Molar specific heat capacity is equal to R by 2. So Q will become NC delta T. So that is NR by 2 into temperature at B minus temperature at A. So we can also write that as 1 by 2 into PBVB minus PAVA. That will be 1 by 2 into product of pressure and volume finally is 2 liter atmosphere. Initially was 1 liter atmosphere. So this is in liter atmosphere. Okay. Let's say we are taking 1 atmosphere again as 1 into 10 raised power 5 Pascal. Therefore, 1 liter atmosphere will be 100 joules. So it will be 50 joules. So Kunj, your answer was correct. Very good. Q is plus 50 joules. That means heat is being supplied to the gas and 50 joules of heat is being supplied to the gas during this process. Okay. Next we come to work done by the gas. That is NR delta T upon 1 minus alpha. So that will be NR into TB minus TA upon 1 minus 3 by 2. So minus 2 times NR delta T or 2 NR into TA minus TB, we can write this. Because the minus sign, you just take it inside. Okay. So we can write this as 2 times TAVA minus TBV. Oh, I think I might have written the final value of pressure wrong. Let's just check it out. Okay, the final value of pressure should be initial pressure into VA by VB. So that is 1 by 4 into TB by TA. This is 1 by 2. Sorry, temperature is becoming half, so this should be 1/8. Just make a correction here, people. The final pressure should be 1/8 of the initial pressure. So it is quite a bit less. So it is 1/8 of an atmosphere. So that is 0.125 atmosphere. Okay. Just make this correction, people. This correction. So that will change these answers. Okay. So Q will be negative actually. And Q should be negative because C is a positive quantity and delta T is negative. So PBVB will be 0.5 minus PAV is 1 in liter atmosphere. So this will become minus 1 by 4 into 100 in joules. So Q should be minus 25 joules. So that means heat is withdrawn from the gas. 25 joules of heat is withdrawn from the gas. So please make a correction to the value of Q also. Kunj, check out where you might have made some mistake because you also got plus 50 initially. I calculated the final pressure wrong. It was not PA by 2, it should be PA by 8. So just make that correction. And from there on, the rest of the things will follow straightforward. So I'm just minimizing this a little so you can see the whole calculation now. Now we'll substitute for this work done. So we'll see that work done is positive because it's an expansion, but Q is negative because delta U will also be negative. So anyway, this PAVA is 1 liter atmosphere, PBVB we just saw is 0.5 liter atmosphere. So this will become plus 100 joules. So work done by the gas should be plus 100 joules, which also means that delta U should be how much? Should be minus 125 joules. So anyway, we'll check that out. Okay, Kunj, have you checked out the solution? Okay, you took degrees of freedom as 3. That's okay. But Q has to come out negative, na? So, acha, C ka value must have got wrong because of. Okay, now it is fine. It's clear. Okay, now let's calculate delta U. Now, delta U, there are two ways of calculating now. We have already calculated Q and W. So, we can calculate it as Q minus W. So, from that, we can see that delta U should be minus 125 joules. Okay. Or we can also calculate delta U from formula, that is NF by 2R delta T. So, it is N5 by 2R into TB minus TA. So, that is 5 by 2 into PBVB minus PAVA. So that is 5 by 2 into 0.5 liter atmosphere minus 1. liter atmosphere. So we can multiply by 100 to get it in joules. So we can see that this factor is half, so it will become 5 by 4 into 100. Okay, but with a minus sign because it's minus 0.5 minus 1 is minus half. So from that, or it is minus 125 joules as expected. So actually you never need to calculate all three things, Q, delta U and W, because once you got two of them, the third you can directly calculate by using the first law of thermodynamics. Okay, this is coming from the first law, that Q is equal to delta U plus W. So as far as the PV graph of this process is concerned, that will look like a hyperbolic curve, but with a very steep slope, because the power of P is 3 by 2 in the polytropic equation. So the PV graph for this particular process will look something like this. A to B, where P is proportional to 1 by V to the power 3 by 2. So compared to isotherm, it will have steeper slope. And you can see if these are isotherms. This is the isotherm at A, then it was isotherm at 400 Kelvin. If this is the isotherm at B, it is 200 Kelvin. So temperature is decreasing as volume is increasing, which means it has a steeper slope. And also you can see that here the pressure was 1 atmosphere. The volume was 1 liter. Now the volume has expanded to 4 liters. Whereas the pressure has come down very drastically to 1/8 of an atmosphere, or 0.125 atmosphere. Okay. So clearly from the graph, you can see that temperature is decreasing, so delta U should be negative, but area under the curve should give us a positive quantity. So work done was positive. But then the delta U is minus 125 and the work done is only plus 100. So overall the Q is negative, which means that we are withdrawing heat from the gas in order to expand it. Okay, so hope this example is clear to all of you. Now we'll move on to cyclic processes next. So a cyclic process by definition is very simple. Its PV curve should look like a closed loop. Okay, that means it cycles and comes back through whatever path to its original state. So that is how we define a cyclic process. It is a thermodynamic process during which heat and mechanical energy work are exchanged such that the gas comes back to its initial state finally. Okay. That means that P final, V final, T final is equal to P initial, V initial, T initial. Okay. Which means that the PV graph, and for that matter, if we draw the temperature volume graph or even the pressure temperature graph, any graph that we draw between the two parameters will be a closed loop. Or a cycle, a closed cycle. So in general, the PV graph will look whatever be the shape, but it should come back to where it started from. Okay. Now we'll see that it could go in this direction and come back also, or it could also go in this direction and come back. Both are cyclic processes. As long as the initial state is equal to the final state, we can define it as a cyclic process. Okay. So just make a note of this definition of cyclic process first. I'm sure you're aware of this also from chemistry, but just for the sake of completeness, make a quick note of this definition. Okay, so just write this down, students. I'll be right back. Okay, so next thing we'll understand is that in any cyclic process, initial state is equal to final state. So what that implies is that the net change in internal energy for the cycle is equal to 0. Okay, because final temperature is equal to initial temperature. So delta U, which is 10F by 2R delta T, this has to be 0. Okay. So which also means that Q for the cycle is equal to W for the cycle. The net heat supplied to the gas during the cycle is, okay, so where delta U cycle is the net change in internal energy for the cyclic process. Similarly, W cycle is the net work done by the gas during the cyclic process, and Q cycle is the net heat supplied to the gas and during the cyclic process. Okay, so as far as application of first law is concerned, these two equations become very important. That in any cyclic process, since we are coming back to the initial state, therefore any state function will have zero change. So remember, internal energy was the state function, whereas work done and heat exchange were path dependent processes, or they were path functions. So path functions will have non-zero value, okay, but state function will have a zero change in a cyclic process. What do you have in class? Oh yes, Rupesh, I will take you to the starting part. Sorry, I forgot. Okay, just when we finish this, we'll come back to the starting part. So we had just done a quick recap of the general polytropic process. Okay, Rupesh. This is what we had seen in the last lecture also. So it was just a basic recap of that concept. Okay. And then after this, I think you have, yeah. So after general recap of polytropic process, we had seen how the four standard processes, that is isothermal, isobaric, isochoric, and adiabatic, are special cases of polytropic process. For isothermal, the value of alpha is 1. For isobaric, the value of alpha is 0. Similarly, isochoric, it is tending to infinity. And adiabatic, alpha's value is gamma, which is Cp by Cv. Okay, and from that we show that all the standard formulae that we developed before can be shown as special cases of the polytropic process. So just go through this quickly once and it should be pretty clear. Okay, Rupesh, yes. And then after this, I think we were into this question which you had joined in. This question is where you started the lecture from, right? Okay, good. Okay, so let's come back to what we're discussing about cyclic process. So let's look at an example for this now. So let us say we have the simplest possible cyclic process that one can come up with, which consists of, say, a triangular shaped PV graph, and that to a triangular shaped PV graph such that we have an isochoric process, okay, then some kind of unknown process, because it's a straight line like that. Okay, so this is our cyclic process. So first we are taking the gas from A to B, which is an isochoric heating. Then B to C is not a standard process because it's a graph which is a linear function of pressure versus volume. Then again, C2A is an isobaric compression. Okay. So let us say that a sample of helium, okay, undergoes the cyclic process ABCA. Okay. Now, given that pressure at A is 0.5 atmosphere, volume at A is 2 liters, temperature at A is 200 Kelvin. Okay. Temperature at B is, let's say, 300 Kelvin. Okay. And also given that volume at C is equal to, let us say, 4 liters. So first of all, we have to find this thing, all the unknown quantities, that is pressure at B, okay, then temperature at C, okay, pressure at C, etc. Then we have to find Q for the cycle ABCA. And from that, we have to find Q delta U and W for the process BC. Now, BC is an unknown type of process, and you will see that if you analyze it, it's not even a polytropic process, because the equation of the line BC is of the type P is equal to some slope into V plus some constant, okay, where the slope is also a negative slope. So y equal to mx plus c kind of graph, where m is negative and c is positive. So you can see that it is not a, so this implies that BC is not a polytropic process. So if it is not a polytropic process, that means that we have to calculate work done by integration PdV or area. There's no other way. There's no formula directly for work done. Whereas obviously delta U is a state function, so we will use formula for that. And that too, it is given to us that it's helium gas, so it is monoatomic gas. So we'll once again make use of that fact also. The degrees of freedom is 3. So try to work out this question now. So once again, you can see it's a cyclic process ABCA. So Q net should be equal to W net for the cycle, and delta U should be 0. But also that out of the cyclic processes, 2 of them are well-known processes, AB and CA. They are respectively isochoric and isobaric. So we can directly use the formula. Whereas the third one, BC, is an unknown process. Okay. But it is, while it is unknown, at least the graph of BC is very simple. It's a straight line. So we can make use of the geometrical, the geometrical interpretation of work done, which is area under the curve. Okay, so nobody got the answer for this yet. Okay, let's try to figure this out. So first thing, see, you have to understand is how you can interpret the information from the graph. So यहाँ पे देखो क्या हो रहा है, pressure at the point A is 0.5 atmosphere. The volume is 2 liters. So that means now at the point C, see, the volume is given as 4 liters. And the temperature at the point A is given to us as 200 Kelvin. And also the temperature at the point B is given to us as 300 Kelvin. So now see, you can see for the process AB, what is happening is isochoric. So temperature is proportional to pressure. So TB upon TA is equal to PB upon PA. So from this you will get that the pressure at B should become 1.5 times the pressure at A. Okay. So this should become, so now we understand the pressure at this point should become 0.75 atmospheres. And also now you can see that the process CA is isobaric. So that means volume is proportional to temperature. So that means VC upon VA should be equal to TC upon TA. So that will tell me that the temperature, the volume has become double. So the temperature should also become double of TA. So it should be 400 Kelvin. So this is how my unknown quantities come out. So the temperature here is 400 Kelvin. Okay. So for this I know the pressure at the point B is becoming 0.75 atmosphere. Okay. Obviously the volume at B is equal to volume at A only, 2 liters. And temperature at C is 400 Kelvin. And obviously the pressure at C is equal to the pressure at A, which is 0.5 atmospheres. Okay. So now that we know this, we know the first part. Now the second part becomes that much easier because Q during the cycle is QAB plus QBC plus QCA. But also Q cycle is equal to W cycle. Now this might be easier to work out actually. Okay. So that is equal to W during AB plus W during BC plus W during CA. I see that compared to this and this will be easier to calculate because we can interpret this geometrically only. So you can see WAB will be 0. This will be area under the graph of BC. So that will be half into sum of parallel sides, that is 0.75 plus 0.25 into perpendicular distance between them, that is 4 minus 2, so that is 2. So this will be the work done during BC in liter atmosphere. Okay. And the work done during CA will be negative because it's a compression. So that will be minus of the common pressure, that is 0.5 atmospheres, into the volume change, which is, or we can write it like this, plus 0.5 into 2 minus 4. So this is during, again, this is in liter atmosphere, but this is during CA. Okay, this is during BC, and this is during AB. So this is the easiest way to calculate Q cycle because we can get it from the graph only. So 0 plus 1, okay, minus 0.5 into is how much, 2. Wait a minute, this should not come out to be 0. So I may be missing out something. Oh, sorry, this is not point. This is not 1. My mistake. This is 0.5. No, this is not 0.25. This is 0.75 plus 0.5. So that's 1.25. So this is the area of trapezium formula. So this will be plus 1.25. Okay, and this is minus 1. So this is the answer in liter atmosphere. So you can convert it to joules. So it's plus 25 joules. So this becomes the answer to the second part. So here, understand what we have done is for WBC, we have calculated area under BC. So this is the process BC. So we've calculated this area, which is the area of a trapezium. So it is half of sum of parallel sides into the perpendicular distance between them. That's how we've calculated the area. Okay. So this A over here is 0.75 atmosphere. B is 0.5 atmosphere. And D is 2 liters. That's how we've calculated this part. This one. Okay. So just I'll minimize this so that you can relate it with the above graph also. So this should make this fairly simple to understand. Okay, and now just based on this, you can complete the third part of the question. The question is almost directly done already from this. Okay, so just complete this question, then we move on. Okay, so hope you have worked out the third part. Okay, so we got Q for the cycle. Now, actually, if you see, we have already got the second part indirectly. Okay. I mean, the third part indirectly, because we've seen W for the part BC was that area, na, which we calculated. So that area was how much? It was 1.25 liter atmosphere. That is 125 joules. So plus 125 joules is WBC. Now for delta U, we have the formula NF by 2R delta T. So that is, we are dealing with the monoatomic gas. So 3 by 2 into PBVB. Sorry, C is the final point. So first let's write it like this. 3 by 2 into NR TC minus TB. Okay. So that we can write as 3 by 2 into PCVC minus PBVB. Okay, so this will become how much? This will become 3 by 2 into, now you can see the graph. Product of pressure and volume finally was 4 into 0.5, that is 2. And initially was 0.75 into 2, that is 1.5. So it's 2 minus 1.5. Okay, in liter atmosphere. So in joules, this is becoming 3 by 2 into 0.5 into 100 joules. So delta U is becoming 3/4 of 100 or 75 joules. This is our delta U during the process BC. So Q during the process BC is delta U plus W. So that should become, plus 200 joules. Now let's also just verify one thing. This Q cycle that we got from here, this Q cycle should also be QAB plus QBC plus QCA. So this QAB we can calculate by formula. Na? It is NCB delta T. So N 3 by 2R into TB minus TA. So it is 3 by 2 into pressure difference into that common volume. Okay. So it is 3 by 2 into that pressure difference was 0.5 to 0.75. So that's 0.25. Okay. And the volume was 1 liter. So this is in liter atmosphere. So this is 3 by 8 into 100 joules. So that Yeah, sorry about the interruption, students. Some major stuff going on here at my place. Anyway, so this Q will come out to be how much for the process AB? You can see it is 37.5, right? Okay. So QAB is that much. QBC we've just seen below what it is. Now QCA, that is NCP delta T. So that is N into 5 by 2 R into TA minus TC. So when we calculate this QCA will come out to be 5 by 2 into the common pressure at A or C into the volume difference. So this will come out to be a negative quantity, and that common pressure was 0.5 atmospheres, and the volume change was minus 2 liters. Okay, so this is in liter atmosphere. So this will come out to be minus 2.5, isn't it? Liter atmosphere. So we multiply that by 100 to get it in joules. So minus 250 joules. So this is our QCA. So now when we sum up all this, we should be getting the same value of Q. That is just a way to verify that our calculation is correct. So from this now, when we calculate Q cycle, should be getting AB was 37.5. BC we just saw was plus 200. This was minus 250. So we have to check our calculation once. We're getting exactly half of this. Should not be the case. Let me try and quickly work out where the error is. So QAB, it's a sample of helium. So 3 by 2 into 1.5 minus 1. Oh, so I think QAB is the one that we have got wrong. Yeah, this is wrong because this was 2 liters, not 1 liter. This is where we made the mistake. So this volume at A is not 1 liter, it is 2 liters. So just this minor mistake here. Okay. So we will see that this becomes 3 by 4 into 100 joules. This becomes 75 joules. Okay. QAB becomes 75 joules. Okay, so that's all right. QAB is 75 joules. QBC we have just seen here, it is plus 200 joules, whereas QCA is minus 250 joules. So now you can see that Q for the cycle by the second process, by the second method, we'll verify what we are getting from this method, that it is equal to W cycle. So plus 75 plus 200 minus 250, that will give us plus 25. Okay, so here we had got this from actually W cycle, and that was plus 25 joules. Okay, now we can see that that is equal to what we are getting from the individual calculation of Q. So that just verifies the fact that in this question, like in all cases of cyclic process, net Q should be equal to net W. Okay. So anyhow, hope this is clear and calculation part is simple. Okay. Now the next thing that we'll understand about cyclic processes is that in general we have seen that delta U for the cycle is 0. So work done by the gas during the cycle is equal to Q for the cycle. But this can be of two types. Okay. So one is where W cycle is equal to Q cycle is a positive quantity. Okay. So and the other is where W cycle is equal to Q cycle is equal to a negative quantity. So there are two different categories of cyclic processes. Okay, so the second category, this one, is where work is done on the gas, because work done by the gas is negative. So that means work is done on the gas and heat is extracted from it, because heat supplied is negative. That means heat is extracted. So this is what is called a refrigerator cycle. It's a refrigeration cycle. Okay. External agent does work on the system to extract heat from it during the cyclic process. Whereas this one, where Q and W are positive, this means that work is done by the gas, okay, and heat is supplied to it. Okay. So that means the external agent is supplying heat and the gas is doing work. So this type of a cyclic process is called a heat engine. It's called a heat engine cycle. So in general, for any cyclic process, W is equal to Q, W net is equal to Q net. But if they are both positive quantities, that means we are dealing with the cyclic process, which is called a heat engine, because we are supplying heat to the system and work is done by the system, or we are extracting work by supplying heat. So basically we are converting heat supplied into work done by the system. Whereas if both are negative, it is the reverse of that. That means we are doing work on the system and extracting heat from it. So that is the job of, for example, a compressor, which is part of a refrigeration cycle. So example of a refrigeration cycle is a compressor. It can be an air conditioner's compressor or a refrigerator's compressor or a freezer's compressor, anything like that. Because example of heat engine is an internal combustion engine. Okay, of course, we will look at Carnot engines also later. But for example, a more everyday example of a heat engine which affects us in our everyday lives is the internal combustion engine, which typically drives most of our transportation systems. It is also called a fossil fuel engine, because the heat generated by combusting or burning some kind of fossil fuel like petroleum or diesel or gasoline is converted into mechanical work, the form of ultimately kinetic energy of a moving car. Okay. Now the next important thing is how do we identify whether it is a heat engine cycle or a refrigeration cycle? So for that we have to look at the direction of the cyclic process. Direction in the sense that whether it is clockwise or anti-clockwise in the PV graph. So we just think of any arbitrary PV cycle, but the direction in which the cyclic process is progressing, suppose it is clockwise. So it's going from A to B and then back from B to A clockwise. Clockwise PV cycle. And again, we see the same process but in reverse. That is, it is going from A to B via this process first, and then coming back from B to A via the upper process. So this is an anti-clockwise or a counterclockwise PV cycle. So we'll understand that this is the heat engine. Okay. And Q net of the cycle will be equal to W net of the cycle will be positive of area enclosed in the loop. In this case, the loop is ABA. Okay. Whereas this one will be the refrigeration cycle. So I'll just demonstrate why that is the case also, but in general, this is the refrigeration cycle where Q of the cycle will be equal to W of the cycle, will be negative of the area enclosed. Okay, so let's first understand why this happens, then we'll come back to noting this down. Okay, so in this, if you see, in the first case, okay, if we take this whole area as A1, okay, so QAB is positive of A1 because AB is the expansion process, so it's positive. Okay, but at the same time, if we take QBC for the same graph, mind you, this is not the second graph, okay, and this area is A2, then QBC we can see is negative of that area A2. Why? Because BA, not BC. Yeah, B back to A. BA is a compression. So the work done should be negative. Okay. So now when we combine the two graphs, okay, so then we can see that for this case now, Q for the cycle ABA is QAB plus QBA. Now QAB was positive of that area Q1 here, and QBC is, so it's positive of area A1, and QBA is negative of the area A2. So it's becoming positive of A1 minus A2. So this is positive of area enclosed by the loop. Okay. So it is positive of E, where in this diagram now, this enclosed area is what we are writing as E. So that's why you can see that clockwise means we are talking about a heat engine. Okay, that's how it's explained over here, this clockwise loop. Okay. So just make a note of this point over here and make sure you understand the graphical representation of the clockwise loop. Now, similarly, we'll do the representation of anti-clockwise loop also, and you will understand this other part also. You can start by noting down this section, that the two categories of cyclic processes, heat engine and reverse heat engine or refrigeration cycle, is also called reverse heat engine cycle. So if you hear the term reverse heat engine, you know it means the same thing as a refrigeration cycle. Okay, so just make a note of this quickly. Then we'll come to the graphical explanation below. Just make sure you note down the definition first. Okay, you can note down this part first, then come to the lower. Okay, so now this series of diagrams below will show you why clockwise process has a positive work done. Why in the case of clockwise process, what is happening, that Q of the cycle is equal to positive of area enclosed by the loop when we are talking about a clockwise PV graph. Now, very similarly, you can see in the case of anti-clockwise cycle. The case of anti-clockwise cycle, what will happen is, okay, QAB, sorry, WAB. This all should be replaced with W actually. So this is actually ultimately equal to WAB plus WBA. So WAB is plus A1. So that's how finally this happens. Now, in the case of the anti-clockwise PV cycle, you can see that WAB is positive of this area A2, where A2 was this area, and WBA is negative of the area A1, where A1 was this whole area. So Q cycle is QAB plus QBA, but that is also equal to WAB plus WBA. So that becomes plus A2 minus A1. So it becomes minus of A1 minus A2. So it becomes negative of area enclosed. Okay. So Q cycle equal to W cycle becomes negative of area enclosed in the case of anti-clockwise loop. Okay. So that is how we can identify from the given graph the PV loop whether we are dealing with a heat engine cycle or a refrigeration cycle. Okay. If the PV cycle looks clockwise, then it is a heat engine cycle, and Q net is equal to W net equal to positive of the area enclosed. Whereas if it is an anti-clockwise PV loop, as you can see on the right hand side, the Q net is equal to W net for the cycle, which is negative of the area enclosed within the loop. So with this information, it becomes very easy to solve any numerical problem involving a cyclic process. And many times we can directly calculate the Q net or W net of the cycle by using geometry to calculate the area inside the loop. Like in the earlier question, we could have directly calculated the geometrical area of the triangle, and seeing that it was a clockwise cyclic process, it would have given us Q net equal to W net equal to positive of the area enclosed within the triangle. So we don't need to calculate W for the individual processes A, B, B, C, C, and all that. If we can geometrically find the area of the loop, area enclosed within the loop, then we can also use this directly. Okay. So with this, we complete today's session and the discussion about cyclic processes. Okay, we will talk about efficiency of heat engines and Carnot engine in particular in the next lecture. And with that, we will wind up this part of heat and thermodynamics, which is first law and its applications. And after that, that will bring us to the third part of heat and thermodynamics, which is heat transfer, which is completely independent of laws of thermodynamics. That is to do with conduction and radiation and all that. And that is also a part which is not common with chemistry, whereas up to this part, everything was more or less common with chemistry. Okay. So that's it for today's session, people. Make sure you revise the notes of this lecture and all carefully, and continuing doing questions from HC Verma and the module. In the next lecture, we will look at some of the questions also from HC Verma and module, and we will also look at efficiency of heat engines and Carnot engines and those kind of things. Okay. So that's it for today's session, people. Wish you all the best.